Hey, guess what time it is, class? It's science time. Now take out your notes and let's get learning. So now the third part is what's called percent composition. And this is really doing the same thing that you've already done before, but we're going to be adding another step to something that you've already done. And this is when you're finding out the formula weight for a compound. And the way that you were able to take the compound, break it down into its individual parts, and find the mass of the whole thing. So we can take this one step further and find out what is the percentage of each of the substances within that compound. So the percent composition is a percent by mass of each element in a compound. And this is when you're making something into a percentage. Basically what you're doing is you're basing it out of 100. So the way you find this out is to find the percent of an element. You take the mass of the element over the molar mass of the compound. In other words, this is the mass of the whole thing, or sometimes called the formula weight, and then times it by 100. And when you multiply it by 100, this is the reason why you call it a percent, because per means by, cent means out of 100. So you're making this as though this compound has a total mass of 100 grams, and you'll find out how many grams of it is of those each individual parts. Now, for the percent composition, if you remember a while back when we went over this information here with the counting by weighing, and we had the compound, the make-believe compound of BIP3. And you went through the process of finding out what is the formula weight for BIP3. So, for the percent composition, we're actually doing the same thing, but we're just adding one little extra step to the process of finding the formula weight. So when you're finding the percent composition, basically the formula is this, is that you have the percent of the element, or sometimes it could be a group of elements, is equal to the mass of the element over the molar mass of the compound, or I'm just going to put down the formula weight of the compound, times 100. Or to kind of simplify it, the percent composition is basically part over the whole. And then make it the percentage, you multiply it by 100. So, the parts are the individual parts. The whole thing would be the weight of the whole compound, or the formula weight of the compound. So basically all percentages are parts over the whole. You're just doing a comparison between those two. So when we had the BIP3, okay, and we assumed that we had 1 dozen of BIP3. Now we assumed that if you have a dozen BIP3, you're going to have 1 dozen. There's going to be 1 dozen of binder clips. You're going to have 1 dozen of index cards, and you're going to have 3 dozen of paper clips. And so we're going to find out the masses of each one of those. So for the binder clips, if you look over here, 1 dozen is equal to 34.41 grams. So this is kind of like the numbers on the periodic table. So all we're going to do is we're going to take 34.41 grams for every 1 dozen, which comes out to be 34.41 grams of binder clips. For index cards were 30.86 grams for every 1 dozen. So it's going to be our conversion unit. So 30.86 grams for every 1 dozen. And you get 30.86 grams of index cards. And then for the paper clips, it was 15.67 grams for every 1 dozen. So 15.67 grams for every 1 dozen, which comes out to be 47.01 grams of paper clips. So of that molecule, I guess you can say here, if you had a dozen BIP3, you would have 34.41 grams of binder clips, 30.86 grams of index cards, 47.01 grams of paper clips. And to find the weight of the whole thing, you just add all these masses together, you end up getting a total mass of 112.28 grams is equal to 1 dozen BIP3. Or you can also write out as 112.28 grams per dozen. Okay, so hopefully you remember doing that. And let's see how close we get to that mass. Was 112.28 grams, sure enough. Okay, so, and when we actually weighed out the whole thing, it came out to be this amount, which is the same thing by taking into account the weight of each individual part to find out the weight of the whole thing. So now what we're going to do is take this one step further. And when you're looking at the, trying to find the percent composition, basically it's part over the whole. These right here are your parts. This is the whole thing. So all we're doing is finding out what is the percentage of binder clips, index cards, and paper clips. So let me show you how to go about doing this. Like for binder clips, you want to take the part that's going to be the binder clips, which is going to be 34.41 grams of it is binder clips, divided by the mass of the whole thing, or the formula weight of the compound. Oops. The formula weight of the compound, which is your whole thing right here. So that's going to be over 112.28 grams per dozen BIP3 times 100. And so when you do that, so 34.41 divided by 112.28 times 100, and you'll get 30.647% of binder clips. So that's your first part of your answer. Now we're going to find out what is the percentage of index cards. So here's your part, here's your whole thing. So you're always comparing the part to the whole. So we have 30.86 grams of index cards divided by 112.28 grams per dozen of BIP3 times 100. So 30.86 divided by 112.28 times 100, and you get 27.485% of index cards. And then same thing for the paper clips. So if you have 47.01 grams of paper clips, that's your part. Divided by the mass of the whole thing. So 112.28 grams per dozen of BIP3 times 100. So 47.01 divided by 112.28 times 100 comes out to be about 41.869% of paper clips. Now, how can you check your work? Because these are the individual parts that makes up the whole, one thing you can do is if you add all these together, it should add it to be close to, it should be 100%, if not close to 100%. Now in this situation, I end up getting 99.974%. which is close enough here. Because we did a little bit of rounding here, this number isn't quite right. But what this means is that if you have 100 grams of BIP3, 30.647 grams of it will be binder clips. 27.485 grams of it will be index cards. 41.869 grams of it will be paper clips. And this is going to play a big role in the next thing when we start getting into empirical formulas. So this is just one more stepping stone that's going to be leading on to something else later on. So if you have 100 grams of BIP3, this will be the mass of each one of those individual parts that makes up the whole thing. So let's go through and do some example problems. Number 1, find the percent composition of each element in, so part A, cuprous sulfide. So cuprous sulfide, cuprous is copper with a positive 1. Sulfide is sulfur with a negative 2. Positive 1, negative 2, you need to have 2 coppers. All right, so the first thing we need to do is basically just find the formula weights. So this is 1A, we're solving for here. So you assume you have 1 mole of cuprous sulfide, which means you're going to have 2 moles of copper and 1 mole of sulfur. So find out how many grams do you have. So basically just look at the flow chart. We have the moles, go to grams. Since we're dealing with individual elements, we need to be looking at the periodic table. So copper, if you look in the periodic table, is 63.546 grams for every 1 mole. And so 2 times 63.546 is 127.092 grams of copper. For sulfur, you look in the periodic table, is 32.066 grams for every 1 mole. So moles cancel out, which means you're going to have 32.066 grams of sulfur. So these are the mass of the parts. So now find the mass of the whole thing. So you add them together, which comes out to be 159.158 grams. Is equal to 1 mole of cuprous sulfide, or it's 159.158 grams per mole. So again, this here, these are your parts. This is the whole. So you're trying to find out the percentage of copper and the percentage of sulfur. So you can always take the parts over the whole. So to find out the percentage of copper, what we're going to do is take the 127.092 grams of copper, over the mass of the whole thing. 159.158 grams, maybe we put down grams per mole, Cu2S, times 100. So when you do that, you end up getting 79.853% of copper. For sulfur, do the same thing. You're going to take 32.066 grams of sulfur over the mass of the whole thing. 159.158 grams per mole, Cu2S, times 100. And when you work it out, it comes out to be 20.147 percent sulfur. So these are your 2 answers here. Now to check, if you add these 2 together, you end up getting, in this situation, we end up getting 100%. Now whatever you do, do not find this one and just subtract it from 100 to get your answer down here. This is, if you do that, you can't check your work. Because if you made a mistake here, and you subtract it from 100, you want to get a value down here, but it may not be the correct one. So this is a good way of checking your work. So what this means is if you have 100 grams of copper sulfide, you're going to have almost 80 grams of it's going to be copper, and a little over 20 grams of it will be sulfur. And again, that's going to play a big role later on. So let's move on to the next one. B, lead 4 chlorate. Lead 4 means it's Pb, positive 4 charge. I'm sorry, it's chlorate, not chromate. Chlorate is ClO3, negative 1. Positive 4 and negative 1, which means you would need 4 chlorates. So you need closed chlorate, ClO3 in parentheses, subscript 4 on the outside, because you need 4 groups of those. So the first thing is you need to find out what is the formula weight for this. So you assume you have 1 mole of it. So you're going to have 1 mole of lead. For chlorine, without this, you would have 1 mole of chlorine. But everything inside of here is being multiplied by 4. So you're going to have 4 moles of chlorine. And then 4 times 3, you're going to have 12 moles of oxygen. So you need to look up the formula weights for each one of those. Lead has a formula weight of 207.2 grams per mole. So 207.2 grams for every 1 mole. This way moles can cancel out. You're going to have 207.2 grams of it is going to be lead. Chlorine, if you look on the periodic table, it is about 35.453 grams for every 1 mole. So 4 times 35.453 is 141.812 grams of it is chlorine. For oxygen, hopefully you'll have this practically memorized by now, it's 15.9994 grams for every 1 mole. Moles are going to cancel out, which comes out to be 191.9928 grams of oxygen. And then we need the mass of the whole thing. So when you add up all these values, we get a total mass of 541.0048 grams per mole of lead 4 chlorate. So again, these here are your parts, and this is the whole thing. So let's find out the percentage of each one of these substances in lead 4 chlorate. So the first thing is we're going to take the mass of lead compared to the mass of the whole thing. So you're going to take 207.2 grams of lead divided by the mass of the whole thing, 541.0048 grams per mole, Pb ClO3 4 times 100. When you do that, you get 38.299 grams of lead. Do the same thing for chlorine. Here's your part, here's your whole thing. So you're going to take 141.812 grams of chlorine divided by the mass of the whole thing, 541.0048 grams per mole, Pb ClO3 4 times 100, which comes out to be 26.213 grams I'm sorry. Shouldn't be grams, those should be percentages. No one caught that. No one told me. You guys weren't paying attention, were you? Okay. Of chlorine. And then, the next one, here's your mass of your oxygen. 191.9928 grams of oxygen, all over 541.0048 grams per mole of lead chlorate times 100. And we end up getting 35.488%, should be percent, not grams, of oxygen. So these should be the total percentage of each one of the substances here, not grams here, percent. So again, if you have 100 grams of lead chlorate, you want to have 38.299 grams of lead, 26.213 grams of chlorine, and 35.488 grams of oxygen. And if you add all these together, you end up getting a total sum of 100%. Okay, and again, you may not get exactly 100%, but you should get something pretty close to 100%. So if you are off by a couple tenths, you should be okay. So let's move on to the next one. C, barium nitrate. So this is part C. Barium is Ba positive 2. Nitrate is NO3 negative 1. So positive 2, negative 1, you need 2 nitrates. So assume you have 1 mole of barium nitrate, which means you're going to have 1 mole of barium. And again, the 2 is being distributed to everything on the inside of here, so everything inside of here is going to be multiplied by 2. So you're going to have 2 moles of nitrogen and 6 moles of oxygen. So you have to look at the formula weights for each one of those. So you have moles to grams. So barium is 137.33 grams for every 1 mole, which comes out to be 137.33 grams of barium. Nitrogen is 14.007 grams for every 1 mole, which comes out to be 28.014 grams of nitrogen. And then for oxygen is 15.9994 grams for every 1 mole, which comes out to be, let's see here, 95.996 grams of oxygen. So you'll have 137.33 grams of barium, 28.014 grams of nitrogen, 95.996 grams of oxygen. And then the mass of the whole thing comes out to be 261.34, roughly 34 grams per mole of barium nitrate. Okay, so now we have these here are your parts, and this is the whole thing. Okay, so let's find out the percentage for each one. So barium is 137.33 grams of barium divided by the mass of the whole thing, which is 261.34 grams per mole of barium nitrate, times 100. And so when you do that, you end up getting 52.0 0.548% of barium. For nitrogen, you have 28.014 grams of nitrogen. Compare that to 261.34 grams per mole of barium nitrate times 100. And that comes out to be 10.719% of nitrogen. And then for oxygen, you have 95.996 grams of oxygen in comparison to 261.34 grams per mole of barium nitrate times 100, which comes out to be 36.738% of oxygen. So here are your answers. So again, if you have 100 grams of barium nitrate, 52.548 grams of it will be barium, 10.719 grams of it will be nitrogen, and 36.738 grams of it will be oxygen, if you have 100 grams of barium nitrate. All right, let's move on to the next one. DFES, which is going to be ferrous sulfide or iron 2 sulfide, part D. So you assume you have 1 mole of ferrous sulfide, which means you're going to have 1 mole of iron and 1 mole of sulfur. So you have to look at the formula weight for each one of those. So iron, 1 mole of iron is 55.847 grams for every 1 mole. We're going to use a calculator on this one here. So you have 55.847 grams of it will be iron. Sulfur is 32.066 grams for every 1 mole. Since you already have 1 mole of it, you're going to have 32.066 grams of sulfur. All right, and then to find the mass of the whole compound, add these two values together, you get a total mass of 87.913 grams per mole of FeS, iron 2 sulfide. These are your parts, and this is the whole thing. So let's work this one out. So we have 55.847 grams of iron in comparison to 87.913 grams per mole of ferrous sulfide times 100, and we have a total of 63.525% of iron. For sulfur, we have 32.066 grams of sulfur in comparison to the whole thing of 87.913 grams per mole of ferrous sulfide times 100, which comes out to be 36.475% of sulfur. So these two are your final answers here. If you add them together, you get basically 100%. So again, what this means, if I were to measure out 100 grams of ferrous sulfide, I would have 63.525 grams of it will be iron, and 36.475 grams of it will be sulfur by weight. Number 2, find the percent composition of the compound and hydrate in cobalt 2 chloride hexahydrate. So in other words, what you're going to do is you're going to find out what is the percentage of the cobalt 2 chloride, this part here, and then hexahydrate separate from the rest of it. So you're going to find out what is the percentage of cobalt 2 chloride and what is the percentage of hydrates. Okay, so the next ones here are going to be a little bit different because you're looking for the percentage of the compound and the percentage of water or the hydrates. So in the first one, we have cobalt 2 chloride hexahydrates. So this is 2A. So cobalt 2 chloride means cobalt has a positive 2 charge. Chloride is Cl negative 1. So positive 2, negative 1, I need 2 chlorides to balance out. Hexahydrates, hexa means 6. So as you go to dot 6 H2O. Okay, so you see we have 1 mole of this compound. So if you have 1 mole of this compound, that means I'm going to have 1 mole of cobalt. I'm going to have 2 moles of chlorine. Now, because this is all one substance here, if I have 1 mole of it, even though there are 6 groups of water molecules to it, that's part of this compound. So this 6 is going to be distributed to for the hydrogen and the oxygen. So I'm going to have 6 times 2, I'm going to have 12 moles of hydrogen. And then 6 times 1, I'm going to have 6 moles of oxygen. So it goes through the same process that you did before, finding out the formula weight for this compound. So the formula weight for cobalt is 58.933 grams for every 1 mole, which means you're going to have 58.933 grams of cobalt. For chlorine, if you look on the periodic table, chlorine is 35.453 grams for every 1 mole, which now gives you a total of 70.906 grams of chlorine. For the hydrogen, hydrogen is 1.0079 grams for every 1 mole. And since you have 12 moles of those, you're going to have 12.0948 grams of hydrogen. And for oxygen, everyone together now, 15.9994 grams for every 1 mole, which now comes out to be a total of 95.9964 grams of oxygen. Now, if you remember with the formula weights, where you can just add these together and find out the formula weight of this, but I want you to do something a little bit different because we're going to find out what is the percentage of cobalt 2 chloride and what is the percentage of water or the hydrates. So one thing we need to do is we need to find out what is the mass of cobalt 2 chloride. So we need to find out the mass of these two. So if you add these two, 58.933 with the 70.906, we get a total of 129.839 grams, and this will be of COCl2, just that part of it. For the hydrate, or for the water, the total sum is 12.0948 plus 95.9964 comes out to be 108.0912 grams of it is water. So you can either add it here or you can add it here. But if you add these two values together here, you get a total of 237.9302 grams per mole of COCl2 6H2O. We're in our room here. So once again, these are here. These are your parts. This is the whole thing. Okay? So what is the percentage of the cobalt 2 chloride, the salt or the compound, and what is the percentage of the water that makes up this whole compound here. So let's go ahead and work this one out. So starting with the, get in frame here. So we have 129.839 grams of cobalt 2 chloride. So 129.839 grams of CoCl2 all over the mass of the whole thing. 237.9302 2 grams per mole CoCl2.6H2O times 100 comes out to be 54.57% of CoCl2. Do the same thing for water. You have 108.0912. And that's of just water, divided by the mass of the whole thing, 237.9302 grams per mole, CoCl2.6H2O times 100. So if you divide these, multiply by 100, you get 45.43% of water. So here's your final answer for that part. If you add these two together, you get a total of 100%. So what this means is that if you have cobalt 2 chloride hexahydrate, if you have 100 grams of it, 54.57 grams of it will be cobalt 2 chloride, and 45.43 grams of it will be water. So that also means that because this is a hydrated compound, if you heat this up and evaporate all the water, make this become anhydrous, basically you're getting rid of the water. So if I measure 100 grams of it, I get rid of all the water on this. This will be how many grams of it will be of this cobalt 2 chloride. Or if I evaporate the water and collect it, this will be how many grams of water I can get out of it. So let's move on to the next one. Part B. We're going to find out the percentage of the compound, magnesium sulfate. So this part here. And then also, what is the percentage of the hydrate, the water part of it here. So what is the total mass of magnesium sulfate? I'm sorry, what is the percentage of magnesium sulfate, and what is the percentage of water in the heptahydrate part of it? And hopefully, that may sound a little bit familiar to you. That is better known as Epsom salt. And this is one where I told you, I want you to do it in a very specific way here because it's going to be, you're going to be seeing this again and again. And so we're just kind of building off of what we've already done here in the past. So this is for 2B, or not to be. I know, dad jokes. So magnesium sulfate. Magnesium is Mg positive 2. Sulfate is SO4 negative 2. Positive 2, negative 2, it's already balanced out. And then heptahydrate means, hepta means 7. Hydrate means water. So for every 1 magnesium sulfate, there are 7 water molecules attached to it. So that is what makes up Epsom salt. So if you have 1 mole of magnesium sulfate heptahydrate, so this is kind of acting as 1 unit here. So if I have 1 mole of this compound, I'm going to have 1 mole of magnesium. I'm going to have 1 mole of sulfur. I'm going to have 4 moles of oxygen. And then, because for every one of these, I'm going to have 7 water molecules attached to this. 7 times 2, I'm going to have 14 moles of hydrogen. 7 times 1, I'm going to have 7 moles of oxygen. Now remember when we went over this with the formula weights, and because you have oxygen here, I told you not to combine these two. This situation, you definitely cannot combine them. So here is your magnesium sulfate, here is your water. So you want to keep these oxygens separate from each other. So you need to look up the formula weights for each one of those and convert the moles to grams. So magnesium, if you look on the periodic table, is 24.305 grams for every 1 mole. Moles will cancel. So that gives you 24.305 grams of it is magnesium. Sulfur is 32.066 grams for every 1 mole. Moles will cancel. It's going to give you 32.066 grams of it will be sulfur. Oxygen, everyone together, 15.9994 grams for every 1 mole, which comes out to be 63.9976 grams of it will be oxygen. And then for the hydrogen is 1.0079 grams for every 1 mole. Since you have 14 of those, you're going to have a total of 14.1106 grams of hydrogen. And then for oxygen, everyone together, 15.9994 grams for every 1 mole. Since you have 7 of those, that comes out to be a total of 111.9958 grams of oxygen. Now, we need to find out for the magnesium sulfate and also for water. So magnesium sulfate, it's this part right here. So if I add these 3 values together, you end up getting 120.3686 grams of it is magnesium sulfate. When you're looking at the water comes out to be 126.1064 grams of water. Now, so we found the individual parts. These are kind of like the a little bit larger parts that makes up the whole thing. Now we need to find out the mass of the whole thing. So when you add them together, you get 246.475 grams per mole of magnesium sulfate heptahydrate. All right, so now these 2 things are your parts, and this is the whole thing. All right, so now let's go through and work this one out. So we have, for the magnesium sulfate, we're going to take 120, get this in frame here, 120.3686 grams of magnesium sulfate. In comparison to the whole thing, of 246.475 grams per mole of magnesium sulfate heptahydrate times 100. And when you do that, you end up getting 48.836% of magnesium sulfate. Then you do the same thing for water. You take 126.1064 grams of water. In comparison to the whole thing, 246.475 grams per mole of magnesium sulfate heptahydrate times 100. And you get 51.164% of water. So here are your answers for that part. And if you add them together, you get, in my situation, 100%. And again, you may not always get 100%. So what this means is that if you measured out 100 grams of magnesium sulfate, 48.836 grams of it will be magnesium sulfate, and 51.164 grams of it will be water. Now, another kind of unusual thing about this is that this is Epsom salt. That means if you were to take Epsom salts and you heat it up very gently, you can evaporate the water off of it. But over half of its mass is actually water, which to me is, I think it's kind of amazing here that if you ever pick up a box of Epsom salts, just think over half of its weight is made up of just plain water. And a little bit less than half of it is actually made up of the compound magnesium sulfate. So even though it's a dry solid, there's still quite a bit of water that's contained within that. All right, so hopefully you understand that. I would advise you again here to practice going over those. Pause the video whatever you need to, and I'm going to have some problems set up on the Moodle for you to do, and they're going to be very similar to this. I would recommend that if you ever get stuck, you're not sure about something, come back to this and review the videos. Or if that doesn't work, then contact me, email me, let me know. I can even do a video conference with you or a group of you as well. But give this a try, and then when you're done with this and you're comfortable with it, go ahead and start working on your Moodle homework. So not the Edpuzzle, but the Moodle. And then we're going to be taking this information and we're going to take this a step further. So that will be leading into simplest empirical formula and then also eventually into molecular formula. So we're not done with this yet. Hopefully all of you are doing well. If you have any questions, make sure you contact me, and stay well, stay safe, and good luck. I'll talk to you later. All right, so we're going to end here, and this is going to be an entirely different area, and so a lot of the stuff that we've already done, we're going to be doing the same thing, but we're going to be working backwards, which is called the simplest formula or the empirical formula. So that will be coming up next.